All right.
I'm going to come to you for physics.
Okay, so here's the deal. I've graded everything I have. I posted the grades today. The mini exam 5, I did not count number 8. Unless you did it, then it was worth a bonus. So I only counted 7 problems. Each problem is worth 10 points. So if you see on here like you had a total of like minus 10 points, then you got 60 out of 70 points. Create the ratio, that's your grade. Then if you did the 8 and you got it right, then I added 10 points, so it would be 70 out of 70, which would be 100. Make sense? So when you get these back, there's no grades on them. It's just how many points I took off. And then I've updated the grades online. I do have, you might have 2 things in here, but I did put them in order, so all of yours should be together. Okay, so please just pass this around. Yes. Yes, I remember that. Yep.
Where did you add those?
Oh, I haven't added it. Yeah. I actually have a couple of bonuses from this class. The ones you're talking about are sitting in my inbox in a special folder that I need to go and look at. And the ones that you handed in are actually taped to my wall in front of my desk. So I'll get to it. Don't worry. Yeah, I have not applied those to anything. I also I did one problem today for online videos for homework. I didn't give you a homework assignment out of 12.4 last time. I gave you a homework assignment out of 12.3. Actually, I emailed everyone because it was at the end of my notes. But for 12.4, what I'd like for you to do is it's actually 2 problems. It's page 720. This is out of 12-4. And number 12 and number 18. Now, those are both even problems, so you can't check your answer, but I did that online in a video. This is a problem where you have to find the center of mass, the center of mass, and the moments of inertia for some lamina. So I talked about it at the very end of class. I didn't get into it. This is an example for you. All right? We good? Okay. All righty. 12.5. So we begin today with triple integrals. So I thought I would take just a quick, brief moment to remind us of kind of like the progression of things here. In Cal 2, we did a regular integral like this, right? And we found the area underneath this. Yep. And so if I ask you here, what is our region of integration? What is our region of integration? What are we integrating over here? You would have to look to the dx to give you some idea of that's the part that tells us about the region. And therefore, it's actually this little line segment, that interval AB. Right? So in a Cal 2 integral, when we're integrating a function with respect to x, our region of integration is a line segment. And line segments are one-dimensional, right? One dimension. Here, last class, we started doing these double integrals, right? And it was like double integral f of x, y, dA, and it was over some region d or r, right? That's what we were using. And so I say, well, what's the region of integration here look like? So you say, all right, well, where did this dA come from? That was the ground, wasn't it? And so that region on the ground was two-dimensional, wasn't it? And that was kind of a difficulty for us, right? Because when we have a two-dimensional region, we started to think about all these complexities we could get here, and so we said, look, let's try and classify these regions. We had type 1, type 2, and then we converted over to polar, right? Well, we had rectangles, which was the easiest, right? Then we went to type 1, then we went to type 2, and then we went to polar, yes? Today, we're going to look at triple integrals. And it's going to be some function of 3 variables that we're integrating. And it's going to be with respect to, let's try and guess. This is dx, x is one-dimensional, just the length of this line segment. dA was the area, which was a region in 2-dimensional space. And this maybe will be what? Volume, right? Some volume of something. It's going to be dV, and so our region of integration is actually going to live in 3-dimensional space. It's going to be some solid here. Now, do not make this, do not confuse this with what we did last time. Last time we were finding volumes of solids between 2 surfaces, right? Yes? The surfaces came from this piece, because we could draw that function and we could have like the top cap and the bottom cap. The ground would be the region of integration. Here, this function takes in 3 inputs and spits out an output. I can't show you this function. We aren't going to be able to see it, all right? So what we will be able to see is its region of integration, but that's it. Do you understand the difference? Pardon? The domain, yes.
The domain of it is going to be a plane.
The domain of a triple integral is a solid in 3-dimensional space. The domain of a double integral is a flat surface in 2-dimensional space, and the domain of a traditional integral from Cal 2 is going to be just a line. So 1-dimensional domain, 2-dimensional domain, 3-dimensional domain. See the difference? Okay. So if you might imagine these probably even more complicated than these, right? We had enough of a hard time dealing with this, right? Now we have a 3rd dimension. So where should we start? Where do you think we should start to make things simple to start with? Like a cube, right? Like a nice box. That's the most simple solid we're going to be able to deal with. So that's where we start today. And very quickly, we're going to realize that not only do these objects get hard to represent, we're going to need additional coordinate systems to do it. So like in double integrals, we use polar to help us out. And so we're going to have to use some more coordinate systems. So we'll have 2 additional coordinate systems that we'll use, cylindrical and spherical. But we'll get to that when we get to it. All right, so triple integrals. A triple integral over region E. So we call that region the domain E. And in this case, let's look at how we are defining the E. Okay, E is a box where your x coordinates are bounded between 2 constants, the y coordinates bounded between 2 constants, and the z coordinate is bounded between 2 constants, r and s. So if I take away this, that was the rectangle from a double integral. We've added in a 3rd dimension and bounded the z between 2 values. And this is what it looks like. Right? So the x-axis is here, the y-axis is here. Here's our box sitting in 3-dimensional space. Does everyone see that our x values are stuck between 2 places? Our y values, so these are x values. Our y values are between 2 places, but now our z values are stuck between 2 constants. Notice that if you take this box and you look at the shadow that it casts onto the ground, all right? So imagine you have a light source up top, and you cast this shadow down. What does the shadow look like on the ground here? That looks like the region that we dealt with double integrals, isn't it? Isn't that just a double integral region? That would be a rectangle from double integrals. Now that's important because of where we're kind of going with this. What's on the ground is going to help us be able to do triple integrals, seeing the shadow on the ground. No questions on this though? Pretty clear? Okay, so if that's our region of integration, what does the triple integral turn out to be? So we have 3 integrals now. We're integrating over that box. We're integrating a function of 3 variables, which I cannot draw for you. Sorry, okay, can't do it. And we're integrating with respect to volume. So that little dv thing, I don't know if I can do this. I don't want to waste too much time, but well, in 2-dimensional space with double integrals, we cut the region up into little infinitesimal pieces, and each one of these little areas was dx dy, wasn't it? And that little dx times dy represented our dA from our double integral. Now, our region that we're cutting up, since it's 3-dimensional, this is a box, but I'm taking a little slice of it, but I'm taking a little cube out of it, like a little sugar cube, right? I'm saying, what's the volume of that little infinitesimal cube? It should be dx dy dz, right? Or dy dx dz, or dz dx dy. How many different combinations are there? Well, let's start with the easiest, okay? The easiest one is to go dz dy dx. This is the way you do it if all your variables are bounded between 2 constants. Can we change the order of integration? Could we change the order of integration when we had constants in double integrals? Yes, right? So it's the same thing with the triple integral. If you have your 3 variables are bounded by constants, then you can actually write this out dz dy dx, or dz dx dy, or dx dy dz. There's five others, so 6 total triple integrals you could do over a box. Your choice. So let's do this one. Evaluate this triple integral, x squared y z dv on 0, 2 crossed with 1, 2 crossed with 0, 1. So these are our restrictions on x. These are our restrictions on y. These are our restrictions on z. That's a box, so I can use the formula I just had up there. I'm going to choose to go dz, dy, dx. That's just my decision. What is it that I am integrating? X squared yz, right? And then my limits of integration, I'm going to go 0 to 2 here. That's my x's. 1 to 2 here, that's my y's. 0 to 1 here, that's my z's. Now, like we did before, we started from the inside and worked our way out, right? So I'm going to go with this inner integral first, and then work my way out. So this should be equal to antiderivative of x squared yz with respect to z is what? 1 half x squared y. I didn't hear you. Z squared. Okay, everyone agree? Evaluated z equals 0 to z equals 1, right? That's the inner integral. And then I'm going to have to, after that, do dy dx. So do you already see that this is exactly what we've done? Just we have one additional integral that we have to do. One additional variable to deal with. All right, let's let z be 1. Nice. Z is 0. Even nicer, right? So this will turn into double integral 0 to 2, 1 to 2. And 1/2 x squared y. That's all we're left with when we plug in 1 and 0. D y dx. And now you're pretty much at what, last class, at the class before, right? You're now at a double integral. So you just go the rest of the way with this. Okay? Just one little additional step. Now, these are the least complicated triple integrals you can ever get. So, of course, we were going to have to make it a little more complicated, right? Any questions, though? Yes?
Are we always going to be given Z? Since, like, if you look down at the domain region, you really can't tell what Z is for the...
Are we always going to be given Z? How do you mean?
The bounds for it?
This?
Yeah.
Oh, no. See, because this is like, again, remember this domain, this E right now is a box. We want our domains to be things that are more interesting than boxes. And so like, take a sphere in the first octant, just that first octant part of a sphere or a ball. You take a ball and just take the piece that's in the first octant. I want that to be E. How do we integrate over that? Because you can't say x and y and z are all between three constants because it's not a box. So that's what's more interesting to us. So we'll see. Hang tight. You'll see how that's going to work out. Actually, it's going to happen like right now, too. All right. All right, so how about a triple integral over region E? So we have a solid, right? I'm not going to tell you exactly what it looks like, but here's what I will tell you. If you take this solid and you cast its shadow down onto the xy plane, its shadow is a type 1 region from a double integral. So here's what I'm talking about. Whoa, why is that so big? Here's what I'm talking about. I have a solid up here, okay? And all I'm telling you right now is that when you cast that shadow down to the ground, that region on the ground is type 1. I mean, that's not working. Screw it. Sorry, I'm trying to rotate this damn thing so you can see it. All right, that's good enough. Is that a type 1 region from a double integral? X is between two constants, y is between two functions of x. Actually, I think I need to reevaluate this. There we go. Okay, so I'm back on the ground. That's type 1. I'll show you our x labels. So our x's are between a and b. Our y values between two functions of x. And now I'll show you the region. I was hiding that from you, okay? But there it is, okay? Do you see, from the top, that's how I get that region, the shadow on the ground. But the z values, okay? The z values are actually stuck between what? Two functions of x and y. See, this is a surface, isn't it? So it's a function of x and y. This is a surface, so it's a function of x and y. So your x's are between two constants, your y's are between two functions of x, and your z's are between two functions of x and y. That is the type of region we're interested in integrating over, at least to start. So this is the way we look at that region. And this is just what I had down here. A is between two constants. Y is between g1 of x, g2 of x. And then z is between two functions of x and y. So we call them normal notation u sub 1 of xy, u sub 2 of xy. If that's your region, if that's what it looks like, then here's the formula for it. the triple integral of some function, oops, that's supposed to be x. The triple integral over the region E of the function of three variables with respect to volume is, well, let me get to this. This is nice. You're integrating the function dz, dy, dx. That's the order, right? But look at your limits of integration, right? They're function, well, except for this. This is constants, functions, functions, right? Do you think you can change the order of integration? No. No, you can't. You have to do it this way. All right, this ought to be fun. Evaluate the triple integral of what function? Y. That's it. The function of three variables up here is just the y function. Nice and clean and easy. dv, where E is bounded by these planes. So we've got to figure out what E looks like first, right? So let's try and draw E. And I've got to try and draw this in three-dimensional space. X, Y, Z. What is x equals 0? X equals 0 is the YZ plane. It's the ground, right? I'll just draw it out here first. There's the ground, right? Hold on. I drew the wrong one first. X is 0, YZ plane, back wall here, yeah? Then Y is 0, XZ plane, which is this wall over here. Kind of closing off the first octant here, aren't I? And then Z equals 0, which is the ground. And then the plane 2x plus 2y plus z equals 4. How should I draw that here? What would be the easiest way to draw that plane? Solve for z, like just move everything around and solve for z? We could do that. Yeah, I like that idea, but we can also, how many points do you need to define a plane? 3 points, right? So just let's find, how about where the plane hits the axes? So where does this plane hit the x-axis? How would you determine that? You set y and z equal to 0, right? So go into this plane, set y and z to 0, and you get 2x is 4. So x must be 2. So I know that one of the points on my plane, which I'm out of colors, so I'll just do it in black, is 2 on the x-axis. How about where it hits the y-axis? Set x and z to 0, right? And get y is 2 also. And finally, to figure out where it hits the z-axis, let x and y be 0, and you get z is 4, which is up here. I have a plane that goes through those 3 points. So what I'll do is I'll connect the 3 points together like this. Do y'all see the solid? Do y'all see that solid? That's E. Does the shadow of E on the ground look like a type 1 region? So let me now look at the XY plane, the shadow on the ground. I hit here at 2, right? Was 1 point. That's this one right here. The origin is this back point, so that's there. And then 2 here. So wouldn't that be the ground? Wouldn't that be this piece right here? Yeah? Now I've turned it so we can orient things the way we're used to seeing them, is that a type 1 region from double integrals? Yes? Yeah, because if we drew, the way we did is we said if we drew an arrow from here to here, and as long as the one on top and the bottom stayed the same as we move from left to right, then it is. But I actually need to know what that is, don't I? Don't I need to know what this function is? This function here is my g sub 2 of x, and then the bottom one is my g sub 1 of x. Do you all follow that? What is g sub 2 of x? Negative x plus 2. How'd you get that? You just looked at it, right? I mean, this is a line, right? Y-intercept of 2, slope of negative 1. The other way you could do that, though, that's the way I would do it. But keep in mind, the other way that you're doing that, or can do that, is that line is this right here, right? And that's where that plane hits the xy plane, right? When you hit the xy plane, z is 0. So if you go back up to this plane and you let z be 0, you get 2x plus 2y equals 4. If you solve that for y, you will get this right here. Understand that? I only say that because if it wasn't as simple as a line, then that's what we would have to do. Questions?
Could you repeat what you just said about solving it?
Okay, yes. So if I have to first understand that this line right here is this line, right? And this line is where that plane hits the xy plane. Anytime you hit the xy plane, z is 0, right? So if I take this right here and I let z be 0, let that z be 0, it's not there, and I solve this for y, you see it? You would get the linear equation which represents that. Okay? All right. Can you tell me what the restrictions on x are here? 0 to 2? So here's what I got so far. I've got x is between 0 and 2. I've got that my y is between what? 0, right? This function here is a flat horizontal line. And then the one up here, negative x plus 2. So this is going to go from 0 to negative x plus 2. The last thing we need to figure out is what our restrictions on z are. And this is where we have to look back to the 3D picture, and we have to figure out what's the top surface, what's the bottom surface. So, bless you. What is the top surface for this region E? It's the plane, isn't it? The plane. This triangle basically is the top of the solid. So how am I going to write that plane as a function of x and y? Solve for z. So take this right here. Now I'm going to draw it. This arrow is representing this surface right here. That is z equals 4 minus 2x minus 2y. Do you agree with that? Now, in terms of the formulas that I just gave you, or from the notes, I know it's hard to see. Our y's, I said, were restricted between g1 and g2. That's why I wrote g1 and g2 here. Our z is restricted between u1 of xy and u2 of xy. So this one is actually u1 or u2? u2, because it's the one on top. So this, I'm going to replace the z here. I'm going to say this is u2 of xy is that top surface, which is the plane. And then what is the bottom surface? What's the bottom of that? It's just the xy axis. XY plane, isn't it? The equation of the xy plane is z equals 0. But that's my u1 function. So u1 of xy equals 0. Understand? And so I can come back over here now and I can say z has to be between 0 and 4 minus 2x minus 2y. How are we feeling about that? All right, so we got to set it up now, right? I need to erase, so I'll give you about 4 more seconds. All right. So I've got to do a triple integral. My limits on x were 0 to 2. My limits on y were 0 to negative x plus 2. My limits on z were 0 to 4 minus 2x minus 2y. Right? What function am I integrating? Y. With respect to z, y, and x. That's it. That's the setup. And now we do the integration. So I'll do the integral now. Do this one. The antiderivative of y with respect to z is yz, right? I said yz, I wrote xz. And then from where? Z equals 0 to z equals 4 minus 2x minus 2y, right? That's what I've got to do. And then I still will need to do dy dx after I'm done. So replace z with this, and then we replace z with 0. Thank goodness for the 0, right? I don't have to worry about that. So just z right here. So we will have equals integral 0 to 2, integral 0 to negative x plus 2, and then what happens if I replace z with that and distribute the y? What do I get? Over y is 2xy minus 2y squared. Yeah? dy dx. And now that is basically what we did a couple of classes ago, right? Should I dot dot or you want me to go all the way? I don't care. It's up to you. So let's take a vote. All the way?
Well, one more step.
One more?
One more step.
What would be the next step?
dy.
Do what?
dy.
Yes, dy. So I would need to integrate this, right? I'm going to do this one right here. So if I take the antiderivative of that with respect to y, I get 2y squared minus xy squared minus 2/3 y cubed. Everyone agree? Yeah? Anyone disagree? We're good? Evaluating where to where? Y equals 0 to y equals negative x plus 2. Right? That's my middle integral now, right? So I have like an inner, a middle, and an outer integral. And then you go in and you replace your y's with this. And then you place your y's with 0. Good, that's nice news. And then you're going to have a huge like polynomial in x, aren't you? And then you just integrate term by term, clean it up, and good to go. Does that qualify as one step, or do you want the negative x plus 2 in there?
No, like you say, it's long.
Yeah. But you're good then? Okay. All right. Easy does it. What do y'all, how do y'all feel about this? Do y'all feel like, I don't know. I was thinking about my Cal 2 class the other day, and like, we're in there, we're like laughing and having a good time, and we're all like, everyone's, and then I come in here and like everyone's so quiet and so, I don't know. Is it miserable? You're just miserable? Okay. I can appreciate misery. All right. All right, so what would happen if I have a solid E? I want to integrate over this solid E, and I look at the shadow on the ground, and it's not a type 1. It's a type 2 from a double integral. Well, the only thing that's going to change is that now your y's are stuck between two constants, right? Y's are stuck between two constants. Your x's are stuck between two functions of y, and your function, right, your solid is still stuck between two functions of x and y. So the only difference in the actual integral is that it's like your x's and y's are going to switch places. Your y's are going to be the outer integral, and then the middle integral will be the x, right? And then your inside integral will still be the z. So in terms of the setup, here it is. So you see that order of integration would change? Only the last two switch. Triple integral xz dv is the integral, where E is the solid tetrahedron with these vertices. I think I should be able to draw that pretty easily. Let's see. X, Y, Z. Okay, the origin is one of the points. Nice. 0, 1, 0 is this point. 1, 1, 0. 1, 1, 0 here. That's on the ground. And then 0, 1, 1. 0, 1, 1. Do y'all see it? Connect them. I'm going to connect some things together here. This point with this point, 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 this point with this point. Do y'all see that thing? I think I have a right angle right here. Do y'all agree? I have a little right angle there. I don't know, for some reason I don't like that drawing, but do y'all see it or not? Yeah? Okay. So that's my solid E. And if I look at its shadow onto the ground, there really is no shadow because it's on the ground. But let's not get like that, okay? You understand what I'm saying, right? Its projection onto the ground is going to be what? Let's see. That base, right? Good. So it's touching at the origin. It's touching at y's 1, which is this point. It's touching at this point, which was 1, 1, which was out here. And so it looks like this. That right there corresponds to that on the ground. Is that shadow or projection onto the ground a type 1 or a type 2? Or both? It's both. It's either one, right? It's your choice. See, if I draw a vertical, right, like this, and imagine moving this left and right, the top and the bottom curves are always the same. So it's a type 1. But if I draw it the other way and move it up and down, then this one on the right and the one on the left are still the same curves, right? So it's my choice now if I want to go type 1 or type 2. I'm going to do type 2 because we haven't done a type 2. So let me treat it as a type 2. If I'm going to do type 2, I'm going to treat that like a type 2. I need to find my constant bounds on y, then the bounds on x, and then the bounds on z will come from over here. So what would my restrictions on the y be? Between two constants, right? 0 and 1. So that's set, right? And now I need restrictions on x, and those should be two functions of y, right? So I'm going to look at this right here as a function of y, and I'm going to look at this over here as a function of y. I think we call them in the notes h1 of y and h2 of y. So what are they? What's this one over here? 0, because that's just constant 0 function. And then this one over here, this comes from this line, right? Which is, just by inspection, y is x. That's y is x. Again, we don't have a plane. Never mind, we can't do it. I was thinking something else. So I need to solve this for x. So this is y, isn't it? Yes.
Never mind.
Sure.
Yeah, we got it.
Doesn't matter what. So when we're doing the left and right functions, when we're saying which one's
Mhm.
on the left, which one on the right, is it kind of the same as Cal 2 when we're looking at it? We go, oh, approaching from the right. This is first, and this is last.
I don't know. In Cal 2, how did you look at it?
Well, when we're doing like y bounds, we're
Mhm.
doing like right to left, then we're doing x bounds, did top to bottom.
Top to bottom. Okay, right to left. So you're saying it depends on how you want to look at it. Yes. If you're saying this way, you're going top and bottom, and then you're saying when you're going this way, it's right and left. And if that's the way you know it, yes, stick with that.
Okay.
Yes. The way I look at it is by just turning my head to the side.
Right.
And I'm just saying this is the bottom, that's the top now. So this is the lower one, that's the upper one.
Right.
So I would say left to right, because I always start with the smaller and go to the bigger. But okay. I don't want to confuse you. Stick with what you know. All right. What do we have still left to do? Because I've got my restriction on x, right? It goes from 0 to y. I need to know what the top of that thing is in the bottom. Any of those you know quickly? Z is 0, the bottom one, right? So this bottom piece in here is u1 of xy is 0. But I need the top piece, this piece. It's a plane, but I didn't give you the equation. But I gave you points. How do you find the equation of a plane if someone gives you points? Well, that was from way back when, right? Chapter 10. So how do we get the equation of this plane right here? You need a point on the plane and a normal vector, right? How do you get the normal vector? Cross product of two vectors that live on the plane. So you got to make sure you get two vectors now that live on the plane. So let's identify some points on this plane. The origin is here, right? This point right here, 0, 1, 1, right? And this point right here, which is 1, 1, 0. You cannot accidentally grab this one. If you grab that one doesn't live on the plane, then it's all over after that. So it's these 3 points, right? Live on the plane. And now I'm going to create some vectors. Doesn't matter, as long as they live on the plane. I'm going to take the vector that goes from here to here. I'll call that vector u1. And then here to here, I'll call that u2. I know you might be sitting there going, don't use u. We're already using u1 and u2. Those are vectors. They are not scalars. So I could have used something else, v, whatever. So the normal vector will be u1 crossed with u2, which for us would be, what is u1? Aren't they nice? Aren't these vectors nice? Because when you go subtract, it's just those two, right, written as vectors. So I have to take the cross product. Remember how to do that, right? You do, I like to write them vertically, like this, and that way I can do the little, remember this thing? Okay, keep it going. The cross product will equal the normal, which is, so how do we get the I component of the vector? Cover up I, determinant of this, so 1 minus, so 1. And then cover up the middle and flip the sign. So negative 1 and
Wait, hold
what,
on. Oh, gotcha.
here, minus here. Okay. Then cover up this one. So 1. That's it. 1, negative 1, 1. We need a normal vector. We need a point on the plane. Do we have a point on the plane?
0, 0.
Let's go with 0, 0, 0. It's the nicest one, right? So the equation I'm using, if you've forgotten because it's been so long, remember that equation? That's the equation of a plane if you know its normal vector and you know a point on the plane. So it's just going to be 1 times x minus 0, so that's just x. And then negative 1 times y minus 0, so that's just minus y. And then c, which is 1, times z minus 0, so this is going to be plus z equals 0. Now just solve for z. Questions? Solve this for z. Negative x plus y. That is the equation of this top surface. u2 of x, y is negative x plus y. Whew. All right. Set it all up now. I should probably fill this out. This is negative x plus y. So I think hopefully you see that really the challenge of this is just getting the integral set up, right? It's getting all this information put together, get your integral set up. After that, it's just integration, right? Triple, 0 to 1, 0 to y, 0 to negative x plus y. I'm integrating xz, d what? Z d x dy. So you have to be careful with that, right? Because your outer or your restrictions on y. And that tells us right there it was a type 2. That switch there. Okay, so I'll offer right now 2-point bonus on your next test, which is the final. Volunteer, raise your hand. Give me the triple integral as a type 1. If we did type 2, you have about 5 seconds to raise your hand. Go ahead.
Okay, is it 0 to what?
0 to
Yeah.
the first one? No. No.
Goes the integral from 0 to x.
No. Okay. No. Nope. That's it. That's too much time.
0 to 1.
Okay.
The second one would be 0 to x.
0 to 1 here. 0 to x. 0 to negative x plus y. Everything else the same except dz, dy, dx. That's if you had left it as a type 1 instead of type 2. The only difference in it is we went this way, right? So x is between 0, 1. Y is between, oh shit, no, hold on. Y is between x and 1. X and 1. That's why it's so important to draw it, okay? Because the switches are not as simple as, do y'all see that? The bottom one is x, y equals x. The top one is y is 1, constant all the time. So everyone gets the extra. No. All right. What's next? What's next? Everything we've done was a solid with the shadow cast on the xy plane. Why did we do it on the xy plane? No one told us I mean, no one says it has to be that way, right? What if you have, whoa, what the hell? Oh, what if you have this situation? Actually, let me put the solid in here so you can see what I'm talking about. Look at this solid right here. Why can't I do that the way that I have been doing things? Yeah, like look, its shadow is a, if you look at its shadow, you are not going to be able to see a type 1 or a type 2 region. Because what happens is as you go up on the sides, try and turn this just a little bit. If I were to try and look at that shadow on the ground, you see this curvature here? I would only pick up that outer edge of the shadow. But there's a lot of things happening in here with my x and y values. They're changing. And so that won't work. I could not do that as a type, or like the ones we've been doing. But if this particular object has a nice shadow going up against the YZ plane, then maybe I can do it. So I could have my y stuck between two constants, my z's stuck between two functions of y, and then I could have my x's be surfaces. Holy shit, right? So you have this case, and then you could have this on the wall be a type 2 region, right? The other way around. And then you could also have a shadow on this wall in two other possibilities. And we aren't going to go through all these. We're going to stick mostly to what we just did. But we want to make sure we understand that you could actually have a solid where your shadow down is no good and you have to look at other ways. All right? I believe I say that here. No, I make you do it both ways. All right. Let's skip that one. Okay, here we go. This looks like a fun one. Evaluate the triple integral of z dv where your solid is bounded by blah, blah, blah. All right, let's give you about 10, 15 minutes, see what you can do. All right? we move on. So I get to draw it, three-dimensional. I have to know what these things look like. So it's enclosed by this cylinder. I gave you the hint that it's a cylinder, but you should recognize that as a quadratic surface. It's a cylinder, radius 3, opens out the x-axis, right? So it looks like this. Radius 3, it's going out the x-axis. So my x-axis goes through here, and of course it extends in that direction forever, but I know that's in here. And then I have x is 0, which is the back wall, right? I'm only in the first octant, so I'm only going to draw this back wall. So the back wall, I have, let me do z equals 0 because it's easier. Z is 0 is the ground, right? Then I have a plane, this right here, this plane, y equals 3x. So this plane, if I look at it on the ground, it's basically the line y equals 3x, which would look like this. It goes through 0. If I plug in 1 for x, what does it spit out for y? 3. Here's 3. So if I go out 1x, I'm going to be here at 3. I don't know, something like that. So I know that that cuts through like that, right? And that line goes forever. And there's a sheet of paper that comes through and cuts through, just like that. Then I have my cylinder. Now my cylinder goes in both directions, but the back wall cuts it off, doesn't it? So if I'm looking at the back wall, it's this quarter circle, isn't it? And as it moves down through here, this plane cuts through it, doesn't it? This plane slices through the cylinder. So if I attach from here to here with the curve, I can see kind of a slice of this thing. Do y'all see how that plane cuts that cylinder? And if I connect these together, it's like a slice of bundt cake. Have you ever had a bundt cake? Kind of like a slice of bundt cake. Not quite, but close enough. Right? That's our region E. I draw its shadow or projection onto the ground. I draw that in two-dimensional space over here. X, Y, it goes through 0. It hits up here at 3. And then over 1, up 3, hits this point. So this right here is that piece on the ground, right? That on the ground looks like a type 1 region to me. I like that as a type 1 because if I draw a vertical segment in there, the top and bottom are always the same curves. My x's are bound between two constants, so I should be able to set up my restrictions on x and y right now. X restrictions are 0 to 1. Y restrictions, so you have to know the equation of this line, which is y is 3x. And then the equation of this line, which is y is 3. It's constant. So this is going to go from 3x to 3. And the last thing now is my restrictions on z. So the bottom of this solid is 0, isn't it? And the top is this part of the cylinder, isn't it? So the cylinder equation is here. You have to take that and do what? Solve for z. You're going to get a plus or minus square root when you do that, but you're only looking at the plus because it's the top. So solve that, you get z is equal to square root 9 minus y squared, right? So this is square root 9 minus y squared. Bless you. And then you set it all up, right? So you'll have triple integral 0, 1, 3x, 3, 0, let's see, square root 9 minus y squared. We are integrating z, d, z, d, y, dx, because it's type 1. And then you go do it. All right. I was just thinking about this. Are there quadruple integrals? No?
Sure.
Not in this class, but I mean, could there be?
Yeah.
Yeah. And if you did it, you could say, okay, well, imagine that we have this, our region, I'll call it, I don't know, E, F, okay? It's a quadruple integral over F of some function of not 3 variables, but 4 variables. I'll say t. D
dv dt.
D, yeah, I mean, like dv was d volume because the E had a volume, right? But what is 1 dimension higher than volume? You know what I'm saying? Like we don't have a nice thing for it. So I could call pretty much anything I want. D, DH, because we could call it a hypersolid. Sometimes a solid that's one dimension higher than 3 is called a hypersolid. I could do that. And what you would have to come up with is restrictions on x, y, z, and t, right? X would be between 2 constants, let's say a and b. Y would be between 2 functions of x. Z would be between 2 functions of x and y. And t would be between 2 functions of x, y, z, x, y, z. So you can generalize this, but we start to lose application because we really only need 3D, 4 really, to work with a lot of things in the real world, 3 or 4 dimensions. So, all right. This is what I was saying. There's different types of triple integrals on, casting shadows on different planes. Now we move on. So if you recall that from double integrals, if you're taking the double integral over d of 1 dA, that this represented the area of d. Remember I said that? If you take a double integral of the constant 1 function over some region d, this answer is the area of the d. Well, it works exactly the same with triple integrals. If you take the triple integral over e of the constant 1 function dv, you get the volume of e. Didn't we just do that problem? Oh, no, we didn't. Sorry, we did not do that problem. That problem is the exact same region, right? That's the exact same E that we just had. But there's not a function that we're integrating, right? It's saying find the volume of that, right? Find the volume. So all I'm going to do is set up the same triple, 0 to 1, 3x to 3, 0 to square root 9 minus y squared of 1 dz, dy, dx. If you integrate that, then you will get the volume of that solid. See the difference? Okay. It turned out to be 3. I just had the computer do it. Now, I think that's where the notes end, right? Is that where they end? I spent some more time today. There's a little more in this section. I have not updated these notes online, but there's some stuff at the end of this section I think is worth looking at. And we won't do an example, but we'll talk about it, all right? That doesn't mean you won't have it for homework. You will have it for homework, but I'm not going to work through one. Application of a triple integral. We saw when we had a lamina last class, if that lamina had a density function, we could find its center of mass. We could find its moments of inertia, things like that. Well, we don't like laminas because we live in three-dimensional space. So, I mean, I'd be more interested in finding the center of mass of some object, right? This is three-dimensional. So if I have an object in three-dimensional space, and I know its density function, then we have the following results. The mass is the triple integral of the density function. Wasn't that exactly what it was with the lamina? The mass was the double integral of the density function. So the mass of a three-dimensional object is the triple integral of the density function. Then we had, with last class, moment functions. But because we were only working with two variables, we had the moment about x, the moment about y. Here, because we have three variables, we have what's called the moment about the xz plane, or sorry, the yz plane. Here's what it is. The moment about the xz plane, here's what it is. And the moment about the xy plane, which is this. So the moment about the yz plane is the same as the mass, with the exception that you have to multiply by x. Moment about the yz plane is the same as the mass, except multiplied by y. Moment about the xy plane is same thing except z. Once you compute all of these, then you can find the center of mass. The center of mass is an ordered triple. It's your x, y, and z coordinates. The x coordinate is your moment about the yz plane over the mass. The y coordinate is the moment about the xz plane over the mass. The z coordinate is the moment about the xy plane over the mass. So there's a lot of integration that has to take place for you to find it, right? But it can be done. Then you have the moments of inertia, which is the object's resistance to motion, to being rotated about something. So if you want to know the moment of inertia about the x-axis, so you have this object, you're trying to rotate it around the x-axis, its resistance to that motion is going to be measured by this triple integral. So do you see that density function again? But you multiply by y squared plus x squared. And then the moment about the y-axis is this, and the moment about the z-axis is this. So you might imagine those could get pretty messy, but they're doable. I have the homework assignment. Yay. I haven't done these on video yet. I plan on doing those, starting those tomorrow. What's your question? What?
It's like on the take home, where we have to find the moments of inertia, on the last one. You said which one is easiest, about the x-axis or about the y? So how do we know? Is it like is it the shortest moment of inertia, or you gotta solve for both?
Someone asked me that question last time.
Did they?
Yeah, right?
And
And I said,
think of a door.
think it,
Oh, yeah,
look
I
it up.
remember that. I remember that.
Be resourceful. I'm sure you can find it out.
No, I just remember that,
Yeah.
that example.
What you could also do if you wanted to try and, I don't know, see what you can do.
No, I got you.
Okay. All right, that's the homework for that section. Got it? We got 20 minutes left. We have enough time to get into the next section. 12:06. Let me save this. So that's it for 12:06. Just do those problems. All right? Triple integrals in cylindrical coordinates. So just like we did with double integrals, we had type 1, type 2 regions. Then we realized, hey, there's some regions that are not very good, as far as they don't look like type 1 or type 2. So we came up with polar coordinates. So now we have this thing with triple integrals called cylindrical coordinates. And here's how it works. It'll look familiar. Actually, it's going to look very familiar. This is just a three-dimensional version of polar coordinates. We use the same exact conversion. X is r cosine theta, y is r sine theta. This is still a relationship, x squared plus y squared equals r squared. Theta equals arctan of z over x, or y over x, is still valid. The only change with cylindrical and polar is that we have a z to deal with now, right? And all we do is let z be z. So we actually don't change z at all. So let me show you. This is what cylindrical coordinates looks like. If I let my theta be between two constants, alpha and beta is what we used, and I let my r be between two constants, I think we used a and b. Oh, that's not a and b. We saw last class that this would draw this polar rectangle. Remember that from last class? That's what this draws. All we're doing now is turning that, and that's the ground, and we're letting z just be z, whatever it wants to be. So I can imagine going around this space. It's still three-dimensional space, but to get around, someone has to give me an angle to turn. Somebody has to give me a distance to walk out, right? And then just a z value, just how high up to go or how low to go. Right? So 3 pieces of information I need to get to a point in this space. R, theta, and z. Do you see how it's just polar with z? Just an up and down now? I remember the first time I was introduced to this, my professor, he was pretty cool. He called this, because we think about Earth, we think about we live in three-dimensional space, right? The planet we live on is a sphere, right? And we'll have spherical coordinates coming up soon. It would be a planet that would look like a cylinder. He called it planet Schlitz, because I guess the Schlitz beer cans or something. I don't know. I just never forget that. Planet Schlitz. Cylindrical coordinates is a beer can. All right, that's what it is. You move around, rotate an angle, move in and out radius, and you go up and down. If you do that, you're going to be somewhere on a beer can. So how does this help us in terms of doing triple integrals? Well, nothing changes in terms of the double integral. So if you think of a triple integral as a double integral with one additional integral inside, then the outer 2 integrals don't change. You still have theta as the outer integral. The next one in is going to be r. And then the inner integral is now going to be your surface top and bottom. That's the big change. Z has to be stuck between 2 surfaces. So last time we were writing u1 of xy, u2 of xy, right? Previous section. But because we're going to cylindrical coordinates, we have to make a polar conversion. Our x becomes r cosine theta, our y becomes r sine theta. Same over here. So here's an example of a region E. Okay, this is what a region E would look like in cylindrical coordinates. See how the shadow of it is a polar region? That's basically what tells you need to be in cylindrical coordinates. If the shadow on the ground isn't type 1 or type 2, and it looks more like polar, then you should convert to Cartesian coordinates, which is what you were suggesting you could have done there. Yeah. On the problem that I walked out and let y'all work on, you could have done polar, but you would have had to project it up against the back wall. Okay. It was possible, yes. Now look at how this triple integral is set up. Alpha to beta is your restriction on theta. H1 theta, H2 theta is your restriction on R. U1 of all this junk, U2 of all this junk, that's your restriction on Z. And do you see the all-important thing in here? R. And that's because anytime you're in polar coordinates, you must have this R here. And Cartesian is polar, just three-dimensional. So do not forget the R in the integram when you go to cylindrical coordinates. We should have time for this one. Find the triple integral over the region E of x dv if E is the region bounded by all this junk. Okay, I get to draw this. Okay, what is Z is 0? XY plane, it's the ground. I might need all the ground. Let's see. It's the ground, okay? But just remember the ground is there, right? I'm not going to draw it. Z equals x plus y plus 5. What is that? It's surface. What kind of surface? It's a plane, right? That's a plane. If x and y are 0, where am I? Z is 5. If x and z are 0, what's y? Negative 5, which would put me over here. And if y and z are 0, x is negative 5, which would put me back here. So if I connect these together, I have this plane, right? It extends in all directions. I have a cylinder, x squared plus y squared equals 4. That cylinder goes up and down, has a radius of 2, which would be, I don't know, 2, 2. I imagine this cylinder going up and down here. This is going to become messy. I'm sorry?
Are there going to be two cylinders?
Yes, there's another one right here. And that cylinder is radius of 3, which is outside of that one. Just a little bit, right? Goes up. They go forever, right? But what the hell does this thing look like? It's the region bounded by all of those. So what about, forget the plane for a second. If it was the region between the two cylinders, it would be, it'd be like a, I don't know, what does that look like to you? Piece of PVC, toilet paper, paper towel roll, whatever, right? That's what it would look like. But you've come through with the plane, and that plane is going to slice through this thing, isn't it? So it's actually going to come through at some angle and cut through this. And when it does it, it's going to look more like this now, right? And the bottom of it is actually the XY plane. So it's just flat on the bottom, yeah? That's the region of integration. It might, so that's hard for me to draw. Do you see? I mean, I'm struggling drawing that. Because it's hard to draw a plane with a slant on a flat sheet of paper. It's hard to draw that. But if I just think through it a little bit, I kind of get an idea of what it looks like, yeah? Now, let's talk about the projection of that solid onto the XY plane. So we can look at the two-dimensional restriction. The two-dimensional restriction of this onto the ground is going to be that thing that looks like a washer, right? And it's everything in here. And when I look at that, I say type 1, type 2, or polar. Polar for sure, which means I need to do this as a triple integral in Cartesian coordinates. So what's my restriction on theta for that region? 0 to pi. What's my restriction on r then? 2 to 3, right? I'm going to go just the points between 2 and 3, radius 2 and 3. And then the last thing I need to get a restriction on is z. I'm going to put z here. What's the restriction on z? 0 to, so the bottom of this is the ground right here. The top of it is the plane. Solve for z, right? So solve this for z and you get x plus y plus 5. Do you agree? Well, it's already solved for z, so I don't have to worry about solving for z, but that's this. Y'all with me on that? We have a little bit of a problem. The issue is that we went to Cartesian. And when you go to Cartesian, it's the same as we went to cylindrical. And when you go to cylindrical, it's the same as going to polar, which means that everything has to, all your x's and y's have to be converted. So this restriction right here should not actually say x plus y plus 5. It should be z greater than or equal to 0, less than or equal to r cosine theta plus r sine theta plus 5. Okay? Understand that? That's everything I need to set up the triple integral. So my integral will go triple, right? You want to go 0 to pi, 2 to 3, 0 to all that nasty stuff, r cosine theta plus r sine theta plus 5. What am I integrating? X. But what's x? I have to convert. R cosine theta. That's it. And then r, because I went to polar, right? I went to cylindrical, which is the same as going to polar. You must have the r in there. And now what are your things out here? dz, dr, d theta. I'd like to do just the first integral, just the first integration. I won't do all of them. Are there any questions, though, on how I did this? Or what I've done? Or why we're here? No? Did it get warm in here? It seems like it got really warm in here. The pressure. Okay, what is the antiderivative of this with respect to z? R squared cosine theta z. R squared cosine theta z, evaluated from z equals 0 to z equals r cosine theta plus r sine theta plus 5 dr d theta. So I now have the pleasure of replacing z with this and this subtracting. The z0 is nice, kills stuff off. The z is r cosine theta plus r sine, that's not so nice. 0 to pi, 2 to 3. Let's see. When I do this to this, r squared cosine theta distributes to each of these. So I get r cubed cosine squared theta plus r cubed again, sine cosine theta sine theta. Am I doing this right? Last one, 5r squared cosine theta. That's it. dr d theta. Now I get to integrate with respect to r. I think I don't have enough time to move on and do more, so let me just finish this off. If I integrate this with respect to r now, I'm going to be in the middle integral now. Antiderivative of this with respect to r is pretty easy to get. So 1/4 r to the fourth cosine squared theta plus 1/4 r to the fourth cosine theta sine theta, and then plus 5/3 r to the third cosine theta. Evaluated 2 to 3. Shit, that sucks. D theta. That does suck. Because I got to replace all my r's with 3 and then with 2 and subtract. I wish it was like 1 and 0. Wouldn't that be nice? But it's or 0 and 1. It's not, though. All right, so I think maybe I'll stop there. I don't feel like doing that. But you understand what you would have to do? When I do that, I'm going to have just constants in front of these, right? And you'll have to integrate with respect to theta. How are you going to integrate cosine squared? Power reducing formula. How are you going to integrate cosine theta sine theta? You could do sine 2 theta or a basic u sub. That's not worth talking about. Right? That's how that would go? Okay. Let me see what's next. Oh, this is the picture of it. This is actually the rendering of that. You can see the solid in there. You see it in there? We found the volume. No, sorry, we're not finding the volume of that. That's just E, all right? And if you do all of it, it comes out to 65 pi over 4. This is almost the same problem, but it's a volume problem. So you're trying to find the volume of the solid between two cylinders and inside of a sphere. So in between these two cylinders and inside this sphere, you're trying to find the volume. You can do that with a triple integral, can't you? You just have to integrate the one function. How would you do that? Can you tell me what the region on the ground would look like? Almost the same exact thing, right? 2 and 4 this time. And then top and bottom. You're going to have to solve this thing for z, right? To get your... Now,
Would you use plus and minus?
I would probably go from 0 to the top and then double the answer. Because it's a volume problem, I would do that.
Set the origin.
Yeah. So it would be something like 0 to 2 pi, because I know I have to draw that whole thing. I know my radius goes from 2 to 4, right? My z restrictions are from 0 to the top of the sphere. 0 to the top of the sphere. The sphere is that solved for z, right? Which was square root of 36 minus x squared minus y squared, right? But I'm in, I keep on saying it, I'm in cylindrical, which is like polar. And so minus x squared minus y squared, that's the same as minus x squared plus y squared. That's really just r squared. So this top piece is just square root of 36 minus r squared, isn't it? Now I forgot, I have to double this because this is a volume, right? I'm integrating what? 1. Then r because I'm in cylindrical. Then dz, dr, d theta. I don't know if you followed that, but that's it right there. Oh, I did it a little different on the computer. I didn't double it. I went to 2 limits. But if you work it all out, I don't know if this works out, by the way. just setting them up is what I'm looking at here. You get approximately 383.595 cubic units, whatever those are. Look at that, I knocked out 12.6. That's your homework. It's only 3 problems. Next class, spherical coordinates. After spherical coordinates, change of variables. Yep.